An electronic digital computer is an automatic machine, meaning, according to Webster, self-acting. And it's true. All you have to do is press the start button, and the computer goes to work. Inside, the control unit directs every step, orders every operation at the proper time, and works in microseconds. But control is only obeying orders that have been given to the computer as part of a process that leads logically from the problem to its solution. There is brain work here, but it is concentrated entirely within one phase, the program, the series of instructions detailing the entire operation step by step. Programming is the work of preparing programs. Programmers are the people who do it. The program process may be divided into 3 steps. Analyzing the problem to determine the factors and the best method of working out a solution. Building a flow chart of the operations to be performed by the computer. And coding the instructions, converting them into computer language. It is the purpose of this film to show in a brief and general way what is involved in these steps. Good programmers know the subject with which the problem is concerned. They also know the computer's methods of operation, its capabilities and limitations. They do not have to understand the electronics and the circuitry, but they do have to understand the functional logic of the computer. Programming involves defining the problem, selecting the method to be followed by the computer in working out the solution, and assembling the raw data to be processed by the computer. As a programmer, you may decide to draw up a process diagram as an aid in getting organized. Such a diagram enables you to set up the facilities the computer will work with: input medium, output medium, auxiliary storage if needed, and source documents. You use symbols to show the various items. The input medium may be punched cards, a file of punched paper tape, or magnetic tape. Auxiliary storage may be magnetic drum or discs, or magnetic tape if high-speed or random access is not essential. The source documents provide the data to be entered on the selected input medium. The output medium may be cards, paper tape, magnetic tape, or reports, which will require the use of a computer system high-speed printer or a typewriter. These symbols, incidentally, have been adopted as military standard. In making up the diagram, you choose the facilities best suited to the problem at hand. Your next step is building the flow chart of the various steps required to process the data. As you decide on the logic to be followed, you construct a chain of symbols that show every operation to be performed from start to finish. These flowchart symbols are from the military standard specifications. This shape is used to indicate the start and the stop of the program process. The rectangle represents an operation, either a transfer, such as moving data from the storage or memory to the arithmetic unit, or the operation may be arithmetic. The diamond applies to logical operations and indicates a decision to be made, a question to be answered, yes or no. This is known as branching and may result in changes of instructions. This shape represents a subroutine, such as table lookup, sorting, or some other set procedure to be followed. A circle with a number in it is used to indicate that the flow goes to another part of the chart to a similarly numbered circle. This is a very simple example of a program flow chart. After start, an operation is to be performed. such as adding two numbers, for example. On the basis of the result, a decision is to be made, such as determining whether the sum is equal to or greater than some given value. If the answer is no, another operation is to be performed, such as taking another pair of numbers from storage and repeating the initial operation. As long as the decision is no, the repetition continues using new data each time. When the decision is yes, a subroutine is to be performed, such as extracting the square root, for example. In the next operation, the result is to be printed out. Stop indicates the end of the program process. Of course, flowcharts are rarely this simple, but are made up in a similar way. The program then takes form in the flowchart, and you build it symbol by symbol, line by line. It may have to be drawn up in sections. Many programs are large undertakings, often requiring weeks or months of work and the combined efforts of a team. The completed flowchart shows what the computer is to do. But information in this form cannot be understood by the computer. It must be converted into computer language. That is your third step, coding the instructions. As the programmer, you may do it, or you may turn it over to a coding specialist. Coding is translating the steps of the flowchart into computer language that the computer can read and store and then act upon. To see in a small way what is involved, let us suppose an operation calls for computing the values of x in this equation, using various given values for A, B, C, and D, and then printing out the solutions. We will follow the process for one set of data, 24, 36, 48, 60. Now the flow chart for this problem is a simple one. The key operations are start, multiply the first two numbers, 24 and 36, multiply the third and fourth numbers, 48 and 60, add the two products, print out the answer, and stop. You begin coding by deciding where you will store the data, let's say in these addresses in the computer storage unit. In addition, you will need to include data transfer operations and to express these instructions in computer language, numerical words. Each instruction word is a group of digits, say 10 in this case. You use the first two to specify the types of operation. By code numbers such as 21 for transfer from storage and multiply, 22 for transfer from storage and add, 23 for transfer from accumulator to storage, and 24 for transfer from storage and print. The next four digits and the final four will represent storage addresses of data. Now the first instruction word is this: transfer from storage and multiply the contents of address 2001 by the contents of address 2002. Note that the instruction does not contain the data to be processed, just the addresses where they are stored. Obeying this instruction, then, the computer will multiply 24 by 36, and if, like most computers, will leave the result, 864 in this case, in the accumulator in the arithmetic unit. Your next instruction word is this: transfer from accumulator to storage the contents of the accumulator, which may be indicated by 9999, to storage address 2005. For the next step, the instruction word is transfer from storage and multiply the contents of address 2003 by the contents of address 2004. The product is 2880. Instruction word number 4 transfers the product from the accumulator to storage address 2006. Word number 5 calls for transferring from storage and adding the contents of 2005 and 2006. That is 864 plus 2880. The next instruction is to transfer from the accumulator to storage address 2007, the result 3744. And the last instruction, number 7, will tell the computer to transfer from storage and print the contents of address 2007. Incidentally, when you make a check run of your coding through the computer, you may order the intermediate products, 864 and 2880, to be printed out by this instruction, so that you can compare these results with a hand calculation. Your coding will include assigning the instruction words to storage addresses, say 6001 through 6007 in this case, using consecutive addresses through which the computer can advance automatically. You use the same coding procedure for the other data to find the other values of X, using different addresses, of course, for the additional data. To assist in the task of coding, many of today's computer systems are equipped to do a good part of the coding themselves automatically. And they will accept instructions in human language, translating it into the computer language required. Self-coding instructions are easily set up. Whole blocks of standard or frequently used instructions can be stored in the computer, ready for use at any time and called upon by special code signals. Thus, electronic digital computers, each year incorporating improvements that increase their versatility and productivity, take on more and more of man's work. But man still does the thinking and the planning, as we have seen, analyzing the problems and devising the programs for the computer.